Is global warming real? Is climate change irreversible? Why are carbon emissions still rising? Join host Dr. Alberto Troccoli, a global leader in climate science and its application to the energy sector, as he unpacks these pressing issues. Through candid conversations with leading experts, get ready to demystify climate change and explore its many layers. So, let's Climunicate!
Hello and welcome to another episode of Let's Climunicate. It's my great pleasure to have with us today Dr. Carlo Buontempo from the Copernicus Climate Change Service, which we will call it C3S from now on, so please memorize it. And I look forward to the discussion and learning more about his knowledge on climate. So we're going to talk about some of the issues around temperature increases now and in the past, and also what the causes of these changes are, and what we're doing, and particularly C3S are doing to disseminate this information and making sure that the authoritative information is shared. So welcome, Carlo.
Well, it's a pleasure to be with you. Thank you.
So, Carlo, you studied physics in Italy, like myself, some years ago. What made you then go into climate? What inspired you to start that profession and career?
Well, in a sense, maybe the odd thing out was to do physics, in the sense that I wanted to work on natural science since I was a kid, and I didn't really quite know what branch of natural science it was. And then I was exposed to physics, and I thought it was a good framing to approach some of the biggest questions. And within physics, I was keen to work on natural science, so I started working on geophysics, on remote sensing in particular, and that's how I got into weather and climate.
That's great. And now you are directing the Copernicus Climate Change Service, so it's a very big task because now C3S has become quite well known around the world, sharing information on climate. So it's I guess a big privilege, but also quite a hard task for you. How do you feel like being at the helm of C3S?
Well, I feel humbled, and I feel the weight of the responsibility more than anything else. As you say, I think it's a privilege. And first of all, it's a privilege to work with so many wonderful colleagues here at the CNWF and within the community. So C3S is implemented thanks to the support of many contractors in National Met Services, in academia, in private companies, and they excel in what they do. So first and foremost, I feel humbled by this excellence that surround me.
That's great. So let's dive into the climate issues then now, shall we? So we have a kind of standard 4 questions that we ask our guests, and these are quick-fire questions just to set the scene, break the ice. So the first question, they're pretty simple, but it's just to show and also to let our listeners know where you stand in terms of climate. So, but can you tell us by how much the temperature has changed in the past 150 years, according to your records?
Yes, well, it all depends on the definition. So, in a sense, the news of the day, the flavor of the month, is the fact that we had the first year above 1.5, so actually 1.6 in our data set. That's 1.6 degrees Celsius above the 1850-1900 baseline. That's the single year. If you look at the longer average, then it's probably closer to 1.3 plus as an average. So we are not yet at the 1.5 with respect to the Paris Agreement, but we are approaching it very rapidly.
Excellent. So of this increase that you stated, what percentage would you say is due to man-made greenhouse gas emissions?
Well, the vast majority. So in a sense, the climate system is a complex system. We know that very well. And there are many, many drivers that plays a role, orbital parameter, volcanic eruption, solar variation. But what we have seen over the last decades, and in particular over the last 10 years, and in particular over the last 2 years, will be very difficult to explain without the additional inclusion of greenhouse gases. So solar irradiance, solar maximum, the El Nino certainly played a role, but this wouldn't be sufficient to explain the peaks in temperature we have seen recently. So to large extent.
Right, and then looking forward, then over the next, let's say, 80 years, normally we'll take 2100 as a kind of target, or 2080, whichever you want to take. Can you tell us roughly by how much the temperature might change?
No, I can't, because while I'm quite confident about what has happened in the past, I don't have the glass ball and to see what will happen in the future. And part of what will happen in the future depends on us. So in a sense, we can, if we are extremely good or reactive to the evidence that we are exposed to, we may be still marginally able to get close to 1.5 by the end of the century. But the upper end can be much higher. And which one of the two or multiple route will take depends to a large extent on our own decisions. So that's harder for me to predict. Maybe I should have done psychology to do that.
Okay, but from what I understand, you are not looking at the decrease in temperature, it's still kind of increased.
Yeah, and that's actually, yeah, absolutely. In a sense, that's probably one of the ways in which we can flip the discussion, because normally when we discuss about climate projections, scientists love to emphasize the uncertainty that there is, which undoubtedly exists. But I would like to actually stress the certainty. So in all realistic scenario, the temperature will go up for the rest for the foreseeable decades. And even a major volcanic eruption, as we have not seen in the last 100 years, can only cool the climate temporarily. So I'm prepared to bet, and I think the majority of climate scientists will be prepared to bet money on the fact that the average temperature over the next 20 years would be higher than the one of the last 20 years.
And the last question, the last quick-fire question is, what do you think is the likelihood that one of the several tipping points that are in the literature, like the meridional overturning circulation, the melting of the ice sheets, or methane thawing, all these things, what is the likelihood, do you think, that one of those will happen over the next 80 years?
Right. Well, I was waiting for the last part of the question, because the first part of the question, without providing a timeline, then is certainty. We do know the climate system exhibit this catastrophic behavior. This tipping point is part of the chaotic nature of the climate system. So we do know from historical record that this tipping point have been triggered, and so it can be triggered again. How likely is for some of those to be triggered within our lifetime? That's a harder question. The general consensus is that some of those are very close to present, and I'm thinking in particular about Greenland ice sheet and West Antarctic ice sheet collapse. And according to some, we may have triggered those already. Now, the response time of these processes are so long that we may not see or feel the full consequences of those for hundreds of years or even millennia in some cases. But the triggering point is very close to present. 1.5 can be a reasonable threshold for some of those. Some other are further away, but even there, since the last assessment report of the IPCC, the consensus is somehow changing. So if you look at the AMOC collapse, I think there is more evidence now than there was 4 or 5 years ago, suggesting that even the AMOC, so the Atlantic meridional overturning circulation collapse, may happen more abruptly and sooner than previously expected. I guess the consensus is still that it's not likely to happen now, but is a concrete possibility that may happen in not too distant future.
Okay, so within the 2100 kind of time frame.
Well, has been suggested by some authors that this could indeed be the case.
Right. Okay. So we went a bit longer with the quick fire questions, but that was worth it. And now we go to the an assessment of some of the questions in more detail. So particularly the temperature. So often we talk about this 1.3, 1.5 degree increase, but that's only for the last 150 years. And there are also, studies that show how temperature has changed over the past thousands of years, 10,000s, even millions, hundreds of millions. There is a lot. We should also remember that only the last 150 years, maybe 200 years, had some solid record of instruments. And before that, it's only something that is a proxy, so it's reconstructed. So it's not really what we observed. But having said that, we hear a lot about this medieval warming, this Roman period warming. So 1,000 years ago or 2,000 years ago with the Roman, 1,000 years ago with the medieval, as well as much higher temperature, maybe 1 million years ago. So how do we place this 1.3 degree in the context of all this record?
Yeah, okay. That's a very good question. And actually, I really like the way you frame it, Alberto, because the first point for me to stress is the fact that has only been recently that we have acquired the capability of observing the climate globally to a high degree. So, and you made reference to 1850 onward as the period for which we can have a reasonable instrumental reconstruction of the climate. But actually, if you look at some part of the southern hemisphere, actually the time series is even shorter. So, a good satellite record only exists from the late 70s, and full characterization of the atmosphere, let alone the deep ocean, but the atmosphere only probably is available from the late 90s. So it's quite recent that we can really have a full reconstruction of the climate system in its entirety. Before then, we rely on thermometer, on station data, and before the mid 17th century, or 16th century actually, mid 17th century, 1600, we actually don't have instrumental record. So we need to rely on proxy, on tree rings, on bubble trap in ice, in glaciers, on deposit, on lakes and the like. Inevitably, we are, first and foremost, as a Copernicus Climate Change Service, a satellite program. So we are very fond of having these resources from satellite, and we don't hold directly paleoclimate records. So in a sense, we need to rely on what the community has done, the work that the community has done in contextualizing the warming that we have since the instrumental record in the broader context of what has happened before. And we do know indeed that the temperature of the climate has changed massively over the years. The orbital parameter have been responsible for large fluctuation in the distribution of the incoming radiation from the sun. Volcanic eruption have disrupted the climate. The Tambora eruption and the year without summer is just a recent geologically example of that, and so on and so forth. To the best of the available knowledge, though, and this can be potentially picked up from the last assessment report, what we have seen in recent years is basically unprecedented. So the last interglacial around 6,500 years ago it is probably not warm enough to compare to what we've seen now. So there is a fairly high chance that what we have seen is warmer than not only the last 1,000 years, but in all likelihood since the previous interglacial 125,000 years ago. So in a sense, looking at paleoclimatic evidence is difficult to see equivalent of the temperature we're experiencing now, since we exist as a civilization.
So, but how much can we rely on this paleoclimate record? Because, as you say, it's and we said it's based on proxy, and it's only the proxy actually comes from isolated places around the world. It's not really the actual global temperature. Like you said, the southern hemisphere has not been very well observed up to about 40, 50 years ago. So how can we rely on point-wise observations only at certain locations and then draw a conclusion about the global temperature?
Well, we can do it because, in a sense, I guess in any scientific discipline, there is not just the measurement itself, but there is also an assessment of the uncertainty around that measurement. And clearly, having a thermometer, or even better, having a very large set of sensors spinning the planet and measuring different quantities and give us a much stronger constraint, and so we can be much more precise on the actual value of temperature we measure today than the temperature we measure or we estimate through proxy 10,000 years ago or the like. Nevertheless, if we do our work well, then that measurement, as the measurement today, comes with an uncertainty range, and then you can compare. Notwithstanding the fact that the uncertainty range of paleoclimate is larger than the uncertainty range of current measurement, we can compare the two. And so even in considering all the uncertainty, the two bars do not overlap, giving you confidence that what you are seeing now is unprecedented on those timescales.
Right. So if we then come again closer to our time, and we discussed before about the link between the temperature and the greenhouse emissions. In the same way as we have a very long record about temperature that goes back millions of years, there is also a record about greenhouse gas emissions, and the two actually correlate very well. So how do we actually demonstrate that greenhouse gas is actually the driver for temperature, particularly in the last 150 years where we have better record, where we have also tools to assess that, and how can we be then certain that there's nothing else that matters in this increase in temperature?
Yeah, well, in a sense, it's not a religion, right? It's based on evidence. We will never be certain for sure. We is on balance of probability and looking at the different drivers. And I guess the first point to say is that greenhouse gases, and in particular long-lived greenhouse gases such as CO2, are an important driver, but are not the only driver. So that's I think we have to acknowledge it, very clearly from the start. I was mentioning orbital parameters. We do know that those play a vital role in changing and driving ice ages and interglacial period over the historical period. We do know that the solar radiation change and modulation, so the 11-year cycle, 22-year cycle of the sun actually modulate the amount of radiation coming to us. And we do know that there have been historical variation in the amount of incoming solar radiation. The same applies to volcanoes and many other drivers. So this is, I think, a good starting point. So if you look at all the things that realistically can play a role, and start from that rather than starting from a preconceived hypothesis. So what can play a role? Well, greenhouse gases play a role, orbital parameters play a role, the total solar irradiance fluctuation plays a role, volcanoes play a role. And then what you should do, and what has been done by many scientists, is to assess what are the variation of those over the historical period. And then you get to variation in the total solar irradiance that are over the last 1,000 years or 10,000 years, probably in the order of 1 watt per square meter. So these are you need to attach number to those, and probably since the amount of minimum in the late 1600, 1700 to now, the variation has been less than 0.1% or so in the total solar irradiance. So we need to look into that and the impact of those on the radiative forcing. you need to look at volcano forcing. So I was mentioning the Tambora eruption in the early 19th century. We got the Krakatoa, we got a few others, but actually over the 20th century we had got relatively few very big eruptions, those that are able to block the sun and reduce the global mean temperature for 2 or 3 years. So this needs to be factored in as well, and so on and so forth.
Yeah,
but fundamentally, I get to the CO2. In a sense, you wouldn't be able to explain the increase in the radiative forcing without accounting to the large increase in greenhouse gases since basically the Industrial Revolution. So for me, that's one of the most convincing evidence of the fact that these represent a very important element. And actually in that, and there is a nice figure on chapter 2 of the last IPCC, I think is figure 210, that looks at the evolution of the radiative forcing and depending on the different sources. So you have nitrous oxide, you have CO2, you have ozone, you have aerosol, you have solar variation in solar incoming radiation, and so on and so forth. But the one that best correlates with the increase in the radiative forcing that is measured is the increase in greenhouse gases, in particular CO2.
So if I understand correctly, you are saying that this can be derived by looking at the radiative properties of these elements and other drivers like volcanoes and so on. So in your reasoning, you didn't imply there was a model involved. Is that correct?
Well, in a sense, there is always a model involved in our thinking, but what that model is may changes over time. So the first paper, we can discuss whether Tyndall or Arrhenius were first in putting numbers on the greenhouse gas effect on the planet. But anyway, the first scientific discussion on the role that greenhouse gases or CO2 emission had in controlling the planet happened in the late 19th century. So you're talking about 1980, 1990. And they had a model, and the model was, a mental model, if you want, on the role that CO2 has, in particular in trapping infrared radiation. So these actually depend on the molecular structure of CO2, the spectroscopic behavior of that gas. And they also linked that the increase in temperature that would derive by an increase in greenhouse gas in CO2. They linked it to an increase in water vapor, which is a very potent greenhouse gas. So, in a sense, the building block were put in that 130, 140 years ago, and really didn't change. The science is that solid. And they had a mental model of it, which provided very accurate projections. And that mental model then became a more complex model, where we account for more processes. We elaborate on that. So model, I think, is a generic word to indicate a way of reasoning about nature. The fact that now we use computer simulations, equations, and other things it's just a tool added to that line of reasoning.
Yeah, you're absolutely right. I mean, there are many models. I was actually referring, I didn't specify, but I was referring specifically to what you said, the numerical models, because as you know, there are also many people that are questioning the reliability of these models. And so it's very good that you can make an argument, like you said, based on maybe not the mental model, but its physical model. It's something that you can prove with physics, and then you can show the spectrum of these gases and then compare with other effects in a quantitative way. And actually, just to for the record, I think there's some records that say it was Eunice Newton Foote, the first person, actually a female, who discovered the effect of CO2. And then obviously Tyndall and Arrhenius, and there was actually at the time of Arrhenius there was also Engstrom, who came up with this theory of saturation of CO2, and some people are still bringing this forward, even though it's been disproven. And And one of the effects of that, I don't know if you want to comment, but is this stratospheric cooling. While the troposphere is warming, the stratosphere is cooling, and this is a clear demonstration that the CO2 is not saturated. So it's
yeah. No, but I think, normally I can go on a rant because on that, because I come from spectroscopy to some extent. So in my undergrad, I work on
That's
a
great.
Raman spectrum of water vapor. So in a sense, you touch something I'm very passionate about, and at times when discussing about greenhouse gases, I really go back to the structure of the CO2 molecule, because it's that simple. It really depends on how the atoms are put together, whether they have an infrared spectrum or not. And so that's why certain center molecules, water for sure, and so CO2 or methane or many others actually exhibit such an important spectrum. And that spectrum is the existence of that spectrum in the infrared, so the rotovibrational property of the model, so how the different atoms move around their center of mass, is the main mechanism driving the greenhouse effect. And this is entirely consistent with what you're saying and what we are observing, by the way. And is the fact that you trap that energy emerging from the planet due to the property of the molecules, and these reduce the amount of energy going upward into the stratosphere. So the cooling of the stratosphere and the warming of the troposphere, I think, is probably the simplest fingerprinting of the greenhouse effect. You wouldn't see the same signature if you were due to variation in the solar incoming radiation. You would see an increase in temperature on both levels, and so on and so forth. So the evidence is very strong. It's very clear. As I said, I'm reluctant to say certainty, because I think all scientists have trained to doubt and to be skeptical about everything. But the evidence is rock solid in this case, and has been rock solid for the last 140 years.
Right. So before we move to the role of C3S, which is the last topic we want to talk about, I just wanted to go very close to present day, because we've seen this sudden increase in temperature, particularly in the past couple of years, and it was actually non-expected. And I think there's still some uncertainty around the cause. So there were some questions around the role of the Hanga eruption a couple of years ago, which this underwater volcano, which acted. Normally volcanoes actually cool the earth, because they are over land, and then they spew these gases that block the radiation. But in this case, the effect was different through water vapor and other things. But maybe that's not the cause or the only cause. So can you tell us a bit more what is going on in the last couple of years, why we've seen this sudden increase in temperature that was not expected?
Yes, and in a sense, I think is a fair comment, and some people in the community have been very vocal about the surprises. I mean, Gavin Schmidt even wrote an article, I think, on the New York Times, stressing how strange these last couple of years have been. Robert Votard, the co-chair of Working Group 1, dropped me a message after, I think it was September 23, when we see that large jump in the global mean temperature, and analyzing the response. The truth is that, okay, it was on the edge of what was deemed possible, but actually model predicted to some extent, or consider this level of warming possible. And I think that's tell us something. I mean, as scientists, we are always fascinated by the things we don't understand, by the things that are at the edge of our knowledge, by the surprises, and that's a good motivation, is what drives science. But I would sort of flip the question around. So there are always surprises, and we will keep working on those surprises to improve our model. But if you look at it from a societal point of view, I would actually argue that models have been incredibly informative and accurate in their projections. And interestingly, I think it was yesterday or 2 days ago, Gavin Schmidt himself wrote a post on Real Climate, looking at how the model projection of the past compared with recent observation, and admitted that actually CMAP3 models, so I'm talking about 20 years ago, were pretty much spot on. And I think that's largely a success of our knowledge. Now, going to the details of your question, yes, there have been several factors that played a role in the high temperature of 24 and previously to the one of 23. For a while, we played with the idea that Hanga Tonga could have played a role in that. Actually, I was quite excited because my PhD thesis was on the injection of water vapor in the stratosphere in the tropics. So I thought that was fantastic. Something that I can test at first hand. In reality, since then, a number of papers came out from different research groups all over the globe. And the result seems to indicate that the net relative forcing of Hanga Tonga has been modest, and the positive forcing due to the ingestion of water vapor or ingress of water vapor in the stratosphere has been to some extent balanced by the aerosol introduced by the volcano. Bottom line, the overall balance seems to be neutral or possibly even slightly negative, depending on the paper you look at. So, good hypothesis, not supported by fact at this stage in time. Other hypotheses that have been flagged were the possibility of a change in the aerosols induced by changing legislation in the emission from ships. Some scientists have been very vocal on that point. Some calculation seems to suggest that this can be an important factor affecting radiation, especially in the busy ship corridor. So I don't know, the UK, France channel or the Southwest Africa and the like. Globally, not likely to be a major source of variation. So I don't think these are probably necessarily the main driver. There are other things, though, that are quite likely to have played a role. One is the fact that we are close to solar maximum, and actually the solar maximum is proving a bit more intense than predicted. So there is more energy into the system than anticipated, and certainly this contributed to it. The other thing was that we have been through not too strong, but still a moderate El Nino. El Nino is a natural fluctuation of the climate system that warms up, as we know, the temperature of the upper layer of the tropical Pacific Ocean, and this is associated to an increase in global mean temperature historically, especially in the months following the peak of El Nino, which happens a bit around Christmas. So, the fact that beginning 2024 was going to be anomalously warm is not strange, considering that El Nino was there. So all these elements have played a role. But there is a nice graphic that we put together for the Global Climate Highlight we published on the 10th of January, looking at the anomalies on top of the trend induced by El Nino. And you see that in the past we've seen larger El Nino, so larger anomaly with respect to the climate of that time. And we hadn't reached the temperature we've seen last year, simply because the climate was cooler and we moved the baseline, and this movement of the baseline is primarily due to increasing greenhouse gases.
Right. So now let's move to the last topic about the role of C3S in all this dissemination and communication and making sure that authoritative information is disseminated and the people who wants to be informed gets the best information. So you develop also a lot of tools, and just as a segue onto the previous discussion onto the C3S, you have this tool that is quite interesting that relies on extrapolation for the global temperature over the next few years, and doesn't rely on this numerical physical models. It's a very simple way, but from what I've seen, that is proven quite strong in the past few years. Of course, it assumes that temperature continues to increase. Do you want to comment on that and then broaden the discussion on the role of C3S? And particularly, I'd like to ask you to tell us some lessons that you've learned in terms of providing this information in a balanced manner, so that we can have also a balanced discussion around the issue of climate, which attracts a lot of polarization, as you know. And with this channel, we're trying to moderate a bit this discussion, and so.
So,
yes.
Do you want me to start from the latter, or do you want me to start from the 1.5 degrees up?
From the tool, so if you can just discuss briefly
Right.
the tool, so that we go from the previous discussion to the tools and then broaden to the.
Well, okay, it's clear that the two are connected. So I can start from the tool that we call it the 1.5 degrees or the Explorer, but actually came out of a simple idea, possibly after work drink with colleagues. And it's as simple as you can get in terms of, we were talking about models before. That's probably the simplest model, is effectively like having a ruler and a pencil, right? And you look at the data and you just trace a straight line that fits the observed data in the best possible way. And then you see where the line goes. Is that the level of simplicity of the tool? But rather than doing with a ruler and a pencil, we have done it with a computer and an interactive display, so that you can see how that extrapolation actually plays out over the historical period, and where it ends. And the other thing we did was to update it automatically. So every month there is a new set of value. And so there is a new estimate, and you see how the extrapolation suggests different dates. Because one of the problems we have with 1.5, and I think there was a paper by Richard Betts a few months ago on Nature, arguing exactly in that direction, is the fact that the definition of 1.5 contained in the Paris Agreement is a retrospective definition. So we will know that we had crossed the 1.5 maybe 10, 15 years later, after having crossed it, which is not very useful. So maybe we will need another definition of 1.5. And what we have done was just to say, okay, assuming that the rate of warming stays the same, then when will the 30 years windows defined the Paris Agreement be, the center of that window be? And that we call that the exceedance of 1.5. And I haven't checked today. I haven't checked recently, actually, but it was in our extrapolation was remarkably close to 2030. So really around the corner, and that's for me one of the elements that I found interesting and I found inspiring of what we do, and is to transform part of the discussion that, as you say, can be very ideological about climate change in something that actually you can touch firsthand. So you can play with the data, you can see where that number ends. And interestingly, and this is probably one of the value of the program, is that the methodology we use is very transparent. I can explain to you in a minute. The data behind is all open and free. You can look at the data yourself if you want, and it's accessible. And that's what we do. So I do see as a primary mission of a program such as C3S to give access to the raw data in a very transparent way. Everything is open and free. You can use it commercially, you can use it for research, you can use it for any other purpose. And we try to attach as much, we call it quality attribute to the data, so objective information about the data set, stability in time, accuracy, precision, known issues, problem, so that you can then, or any other user can then take an informed decision and use that data in the way they feel is more appropriate. So I applaud your attempt to demystify, but also make the discussion around climate change less ideological. At the end of the day, it is about data, it's about observation, it's about things that exist that are in reality. So, you were saying, this estimate of 1.5 doesn't come from a model, it comes from observation. I think that's an important element, right? So, these are facts, whether we like it or not. A journalist, maybe last week or the week before, asked me about politics and climate change, and I don't think actually there is a connection with observation. The fact that the sea level is going up 3 millimeters now, probably more, 4 hours, in excess of 4 millimeters a year. That's a fact. It's not left or right politics. It's just a fact, and whoever we decide to elect as a politician will have to cope with that fact. And the fact that this observation, this data is available for anyone to use and scrutinize, I think actually is an asset as a society we should be able to use better than we had so far.
Excellent. I'd just like to complement this by saying that we didn't mention it before, but I think we should mention that the Copernicus Climate Change Service is a European program. It's a very large European program funded by the EU. So it's and it has a lot of support, and that means that there is a lot of people behind making sure that the data are of good quality, that like you say, it's available also, so anybody can go and check it. And so I guess you would encourage people also to access the data, and if they spot anything, to report it, so things can be improved.
Yeah, well, thank you very much, Alberto, actually, because this saved me from a slap of my end for not having mentioned the European Commission and ECNWF, which is the organization that actually implements the Climate Change Service on behalf of the Commission. So thank you for that. And indeed, you also give me the opportunity to stress this element that you just said in relation to the users. So the data is open and free, but also we are fully operational. And being operational also means that we have a user support that can answer queries or help you in using that data, but to whom you can also report issue or problem. And now we have hundreds of thousands of users all over the globe. So when something goes wrong, we know rapidly, which improves the quality of everything we do.
Excellent. So thank you very much, Carlo, for sharing your insight and for the work you do. And please, everybody, go and have a look at the climate change website, the Copernicus Climate Change Service, and keep up with the great work. Thanks again, and hope everybody enjoyed this episode of Let's Climunicate. Bye.
Thank you, Alberto.